Hello, everyone. I'm Dave Bowick. I'm a principal at Blackwell Structural Engineers. I knew I was going to be in good company today, but I wasn't prepared to be blown away quite the way I have been, and I'm feeling like perhaps I don't belong in the room. But it's going to be very fun nonetheless. At Blackwell Engineers, our practice. We're very much a teaching firm. I mean, we're practice, and we build stuff, and that's what we do. But I and my colleagues have taught in really every university in Eastern Canada, from Laurentian to Dal, to Toronto, Waterloo, Ryerson, OCAD. And we enjoy working with architects. The reason we like working with architects, as engineers, it's not that any of us have an art or architecture background. But as engineers, the best engineers like solving the hardest problems, and the best problems for a structural engineer come from the world of architecture. I define the design as the union of problem definition and problem solution. And from my world, generally, architects live in the problem definition sphere, and engineers live in the problem solution sphere. So we spend our lives trying to find our ways of executing an architect's vision. And so we are in a supporting role, and it's a rewarding role to be in. I thought of a more Canadian, a good Canadian metaphor of a game of curling, that we're the sweepers. The architect launches the rock, and it's our job to lubricate the surface and to get the obstacles out of the road. And that is the contribution that I would like to make to this group. In fact, as an engineer, what I realized that a decade or so, or God knows how long ago, that the engineer's job is really to apply scale to pre-existing solutions for buildings. That engineers were rarely doing anything new. We were just scaling existing things. We scale existing beams, we scale slabs, we tell you how much rebar that goes in them. I don't find that particularly interesting. My personal interest is more at the craft level. I like seeing how things go together, and it's much more interesting to figure out something that hasn't been figured out before than to figure out something that has. So in the context of living architecture, I was trying to think of what are the things that would distinguish this project from a building project, and there are a number of things. One is complexity. We're anticipating things that are not necessarily simple and orthogonal. We're expecting structures that are dynamic. That may mean that they're kinetic and actually have to move. It may mean that they're transformable. It may mean that they're flexible and just need to accommodate very large movements. So there's a departure from normal building structures, which are necessarily static. And they're potentially at a different scale. Scaling is something that structural engineers really struggle with. Try and find a structural engineer, and architects in the room will know this, to advise you on furniture design. Forget it. You'll wind up with half-inch thick plates and 4-inch HSS in order to build a table. So these are the things that depart from conventional practice. Look at a few examples of projects where we are already doing this. This was a building, the Longhouse for the Native Child and Family Services by Levitt Goodman Architects, and they came to us with an idea. They wanted to do a modern version of a native longhouse, and did we have any thoughts? And I'd been impressed by lamella structures at the time. Coastal Studios at Dal were doing some interesting picnic pavilions and things with lamella structures, and I thought that maybe we could just figure out a way to wrap it around a spherical end to resolve the grid into the spherical end. And the only way I could think to describe this was in a 3D CAD model, so I submitted it, and Levitt Goodman passed it on to the fabricator who built from my model. I don't think we ever did any drawings. This is the Bergeron Center for Engineering Excellence at York University. OVARP, we're the structural engineers for the building. We were asked to participate in the facade because the facade is extremely complex. It looks complex here, but in fact it's much more complex than it looks because it's not a ruled surface that's wrapped around a curve. It crinkles, and so nothing is true to the plane. So we were asked if we could propose a way of developing a solution for supporting the facade. You can see it a little bit better here. It was intended to look completely random with a high level of regularity. Daniel Hamilton was a mathematician who developed the patterning of the triangles. So what we contributed on this project, we developed a way of panelizing, making very regular panels within the cladding system, each panel supporting the random window. So this is one of the panels, and then we modeled all of this in SolidWorks in three-dimensional and 3D, supplied the fabricator with a fully resolved 3D geometry, which took essentially months out of the construction schedule because they had no geometric coordination to do in the preparation of their shop drawings. This is literally a kinetic project, one that we're working on with Andrea Ling from the Design Guild, a series of spinning tops. One of the things we really enjoy working on is art, because art presents us with a whole lot of new problems to solve, things that we wouldn't have necessarily seen before. Let me show you this project. This is is just about to be constructed in Oakville. In some ways, it's a very simple tensile fabric structure. Two big hyperbolic paraboloid sails. But we've incorporated just about every complex condition that we could think of into this one little project. And the thing that's really relevant in some ways is that we've really stepped beyond our roles as engineers and are dictating the fabrication details and not just the member sizing, and had to fully resolve this one as well, right down to the nuts and bolts. I mean, it's interesting that the world only went 3D around the year 2000. Engineers only caught up to that about 2010. So we were in a 2D world prior to that. There's some of the complex conditions that we had to resolve. I've been playing with the notion of what I'm referring to as anthромimicry. We derive a lot of design solutions from biology, and we've talked a lot about that, but we also take inspiration from human endeavor a lot as well. The pneumatic tire is a means of taking something that is extremely strong but flexible, which is air, extraordinarily strong air. You wouldn't think so. Combine it with something that is very weak but stiff, which was rubber. Rubber is extremely stiff right up until it buckles, which is right away. You combine those two things with a little bit of pre-stress, and you get something that's both rigid and strong. This project, you can't tell from this view, but there's a 100-foot clear span above curtain wall. We used the notion of the pneumatic tire to take a very strong beam that was far too flexible, and pre-stressed it with cables, pulled it down flat to make this long span impossibly thin. This is the Ontario Celebration Zone, Hariri Ponarini, inflatable tubes. Another nice little pavilion project. What I wanted to draw your attention to here is the granularity. So it looks like we're out of time, so I'll just flip through the images. This is developing grid shell forms using software modeling as opposed to physical modeling. And there's an actual built grid shell with one of the fabrication details. And then lastly, the Assiniboine Park Conservatory, which will be built starting next year in Winnipeg. A cable net with ETFE pillows. And this is a spiral on radial grid. And when I talk about anthropomimicry, the grid form is the same form that's used in the lacrosse stick, the native lacrosse stick. So thank you for paying attention to my speedy presentation.